Mark. Today's my presentation title is Charge Pumping under Electron Spin Resonance. First, I'm talking about defects or dangling bonds at the silicon-silicon dioxide interfaces. This figure shows the silicon cross-sectional view of silicon MOS transistor. As you may know, source drain current is controlled by the MOS gate. So the current flows at the silicon-silicon dioxide interface. Therefore, some of electrons are captured by the interface defect states. And the trapped electrons emitted to the channel randomly. So it has been well known that these interface defects make a degradation of MOS performances. On the other hand, recently, from the viewpoint of the quantum information field, it is demonstrated that the electronic charges and spin control by using the interface defects. In that case, the defects work as an experimental host. Therefore, a precise evaluation of interface defects is more and more important for MOS interface reliability and for quantum information field. So far, there are several defect evaluation methods have been proposed. One of them is the charge pumping method. As I will introduce later, about the charge pumping is a widely used method for analyzing defect electrical properties. However, there are some problems. So in order to clear the problems, we combine the charge pumping method with electron spin resonance method. We call it charge pumping ESR. Especially here, we call it charge pumping electrically detected magnetic resonance method, charge pumping EDMR. By using charge pumping EDMR, we for the first time identified the defect origins responsible for the charge pumping method. We also clarified the detailed charge pumping process by using charge pumping EDMR. In this presentation, first, I'll talk about the charge pumping method. This figure shows the setup for the charge pumping method. The point is that a pulse voltage is applied to the MOS gate. And when a positive bias is applied to the gate, source drain electrons flow into the channel, and some of them are captured by the defect state. And subsequently, negative bias is applied to the gate, or flow into the channel come from substrate. So the trapped electrons recombine with hole come from substrate. Therefore, recombination current flow. This current is called as a charge pumping current and is proportional to the defect density and elementary charge and gate pulse frequency. So by measuring the charge pumping current, we can estimate the defect density by using the charge pumping method. In more detail, I'll show you the charge pumping process in one cycle of the pulse. When a positive bias is applied to the gate, conduction band electrons are captured by the defect states, and subsequently, negative bias is applied to the gate, trapped electrons recombine with valence band hole come from substrate. So in charge pumping method, recombination process are controlled by the MOS gate pulse. Here, I will introduce how to evaluate the defect density. Especially here, I will introduce pulse-based voltage sweeping method according to this literature. This figure shows the charge pumping current as a function of base voltage. This figure shows the typical charge pumping characteristics. Here, the base voltage is the bottom of the pulse, as shown in this figure. As we can see, region 1 and region 5, charge pumping current does not flow. This is because that, for example, in the case of 1, bottom and top voltages are below the flat band voltage. So only hole flow into the channel and flow out of the channel. Namely, electron does not flow into the channel. Therefore, electron-hole recombination current does not flow. Similarly, in the region 5, bottom and top voltages are above the threshold voltage. So only electron flow into the tunnel and flow out of the tunnel. Hole does not flow into the tunnel, so the charge pumping current does not flow. However, at the region 3, hole flow into the tunnel and electron flow into the tunnel, so the electron-hole recombination current flow via defect states. Actually, in the experimental data, from the maximum charge pumping current, we can estimate the density of states as shown in this figure. By using charge pumping method, we can also obtain the information of interface information of the density of states. I'll skip the detailed explanation, but by changing the gate pulse slope, we can obtain the information of density of states in the silicon band gap, as shown in this figure. For example, for the gradual slope, defects in the narrow energy range can be detected. On the other hand, for the steep slope, defects in the wider energy range can be detected. So by changing the gate pulse slope, we can obtain the defect density at our energy level. Moreover, by using the charge pumping method, we can detect single defect. By measuring the MOS transistor with a single defect, we can obtain the charge pumping characteristics as shown in this figure. This figure shows the charge pumping current as a function of base voltage. The point is that the current is equal to the 0.16 picoampere. In this case, the gate pulse frequency is 1 megahertz, so the detected of number of spin is 1. Therefore, this current plateau shows the recombination current by a single defect. Namely, charge pumping is sensitive to the electronic charges. So there are many advantages in charge pumping method. However, there are two problems. One problem is defect origins. As I mentioned in previous slide, charge pumping is sensitive to electronic charges. However, charge pumping method is not sensitive to the electronic spin. Therefore, we cannot identify the defect origins responsible for the charge pumping method. In other words, we don't know which kinds of defect response contribute to the charge pumping process. Another problem is the charge pumping process. According to the widely accepted literatures for density of states for silicon-silicon dioxide interface, 2 electrons are captured at our defect site. Namely, single electron, first electron is captured at a lower energy level, and second electron is captured at a same defect site at the higher energy level. Namely, 2 electrons are captured at one defect site. Therefore, we cannot simply explain the charge pumping process, namely, one by one electron hole recombination by one defect site. Therefore, detailed charge pumping processes have not yet been clarified yet. So, in order to clear these two problems, we combine the charge pumping method with electron spin resonance method. Then I'll talk about electron spin resonance method. This picture shows the conventional electron spin resonance system for expanded 10 gigahertz. You can see the electromagnet and electron spin resonance cavity. This figure shows the setup for the ESR method, electron spin resonance method. Sample is put into the ESR cavity. Here, we apply the magnetic field and microwave. The point is that the microwave frequency is fixed. Namely, microwave energy is constant here. But here we change the magnetic field as a parameter. So by applying the magnetic field, the defective state is split into two states by applying the magnetic field. This is called Zeeman splitting. At a lower magnetic field, the microwave energy is smaller than the splitted energy, so there is no electron spin resonance. But at a middle magnetic field, the splitted energy is equal to the microwave energy. The electron spin resonance occurs. Moreover, at a higher magnetic field, the splitted energy is larger than the microwave energy. So there is also no electron spin resonance process. Therefore, we monitor microwave intensity as a function of magnetic field. Microwave absorption can be observed at the resonance field. Actually, we monitor the microwave intensity using the lock-in amplifier, so the differential signal is obtained as shown in this figure. From the resonance field called G-value, we can obtain the information of defect structure in a sample. Let me show you the ESR spectrum for silicon as an example. Lower figure shows the ESR spectrum for a bulk silicon sample with silicon dioxide film. Horizontal axis shows the magnetic field. As we can see, two clear peaks are observed in the spectrum. Left side peak is due to the interface defect called PB0 center, which shows red crosses as shown in this figure. Right side peak is due to the oxide trap called E prime center, which shows green crosses as shown in this figure. So by using the ESR method, electron spin resonance method, we can identify the defect origins, namely defect structure, as shown in this figure. For the charge pumping electrically detected magnetic resonance method, the charge pumping is conducted under electron spin resonance condition. So the transistor is put into the ESR cavity, as shown in this figure. The point is that in conventional ESR method, microwave absorption is detected, but here we monitor the charge pumping current, as shown in this figure. By measuring charge pumping current, we can detect only the defect in the current path selectivity. So this is a very high sensitive method. This figure shows the charge pumping current as a function of base voltage, as I showed in previous slide. Here we monitor the constant charge pumping current with the base voltage fixed, as shown in this figure. Then we see the magnetic field. Of course, at the out of resonance, the charge pumping current is constant. At the resonance, the charge pumping current is slightly changed. Namely, this current is slightly changed at the resonance. The change in current is about 10 to the minus 5 to the charge pumping current. Therefore, very small current should be detected. So we monitor the current by using lock-in amplifier. The differential signal is obtained as output as shown in this figure. From the resonance field called G-value, we can obtain the information of defect structure responsible for the charge pumping process. So let me show you the results of the charge pumping EDMR at room temperature. As we can see, clear peak is observed in the spectrum. From the resonance field or G-value, this signal origin is identified this signal origin to the dangling bonds at silicon-silicon dioxide interface called PB0 center. We then estimate the sensitivity. This figure shows the differential spectrum as I showed in previous slide. We integrated this signal with respect to the magnetic field. So this is the original signal or integrated spectrum. The signal intensity is 100 femtoampere and the noise is 101 femtoampere. Therefore, the signal to noise ratio is 100. From the charge pumping current, total number of spin is 10 to the 4. Therefore, a detectable number of spin in our present measurement system is on the order of 100 spins. Then we measured the low temperature charge pumping EDMR. This picture shows the low temperature EDMR system. By using the refrigerator, we measured at 10 Kelvin. We measured the conventional N-type silicon MOSFET. The details are shown here. So let me show you the result of charge pumping EDMR at low temperature, here at 30 Kelvin. You can see several peaks are observed. We integrated this signal with respect to the magnetic field. This is an integrated signal. We deconvoluted this signal into 3 peaks, as shown in this figure. We then identified this signal from the resonance field. And the red peak is due to the interface trap called PB0 center. Green one is due to the oxide trap called E prime center. Blue one is due to the energetically shallow state. This is due to the interface roughness. So we found that 2 kinds of defects are responsible for the charge pumping process. We then confirmed these 3 peaks are responsible for the charge pumping process by measuring the gate pulse frequency dependence of the signal intensity. This figure shows the charge pumping EDMR spectrum for the various gate pulse frequencies from 3 kHz to 5 kHz. As you can see, the signal intensity or signal height increases by increasing the gate pulse frequency. We plot the signal height as a function of gate pulse frequency. In the right side of the figure, red, green, blue shows the PB0, E prime, and shallow state. Black shows the charge pumping current. So as you can see, peak heights are proportional to the gate pulse frequency. This means that PB0, E prime, and shallow states are surely responsible for the charge pumping processes. Finally, I'll talk about the charge pumping process. In the conventional EDMR method, not the present charge pumping EDMR, the observation of the signal is due to the formation of the spin pair. In this work, we also attribute the observation of the signal to the formation of the spin pair. For example, PB0 defect center is closely located at the shallow state. These 2 states form the spin pair as shown in this figure. And once these 2 electrons are captured at the triplet excited state, no recombination process occurs because of the higher energy states. So charge pumping current does not change here, but by sweeping the magnetic field, and at the resonance field of the PV0 center, electron spins at the PV0 center is flipped, as in this figure. So this triplet to singlet transition is allowed to be relaxed down to the ground state singlet state. This enhances the recombination rate because of the energetically lower states. So the charge pumping current increases at the resonance field of PV0 center. For the case of the spin pair of between the E prime center and shallow state, similarly, at the resonance field of E prime center, the electron spin of E prime center is flipped. This triplet to singlet transition also enhances the recombination rate. Therefore, we can observe the increase in charge pumping current at the resonance field of E prime center. Not only defect spins, but also shallow state spin is also flipped at the resonance field of shallow state. Similarly, this triplet to singlet transition also enhances the recombination rate. Therefore, a shallow state peak can be observed. Namely, the observation of the signal is due to the key to the observation of spin pair. Observation of the signal is the formation of the spin pair. The formation of the spin pair is supported by the temperature dependence of the signal intensity. This figure shows the spectrum for various temperature from 30 Kelvin to 300 Kelvin. As you can see, signal intensity changes by changing the temperature. We plot these signal heights as a function of temperature, as shown in this figure. Left side figure shows the signal intensity for defects. Right side figure shows the signal intensity for shallow state. The point is that the temperature dependence are the same with each other, and the shallow state signal intensity decreases at a higher temperature because shallow state is energetically shallow, so the electron emitted to the conduction band at a higher temperature, so the signal intensity decreases. Similarly, defect signal intensity decreases. Moreover, the signal ratio of shallow state to defect state is on the order of 1. This means that shallow state forms a spin pair with defect state 1 by 1. Therefore, shallow state forms a spin pair with defect states as shown in this figure. Here, note that the shallow state is not the recombination center, but the electron supplier to the defect state. Here, I'll summarize the charge pumping model. First, by applying the positive bias to the MOS gate, first electron is captured to the defect state, and second electron is also captured at the same defect site. And negative bias is applied to the gate. These two electrons recombine with valence band hole 1 by 1. Here, a second electron capture and recombination process is spin-dependent process, as I showed in previous slide. In conclusion, spin-dependent recombination is explained by the formation of electron spin pair, and the charge pumping by defects is 2 electron processes. Finally, I'll touch on our recent work. This figure shows the charge pumping EMR spectrum, differential spectrum, and integrated spectrum, as I showed in previous slide. As you can see, PV0 E prime shallow state peaks. But we measured another devices that the defects generated closely located at the nearly at the arsenic donor atoms. By measuring this MOS transistor, 4 additional peaks are detected. This is also explained by the formation of the spin pair, namely defect spin forms the spin pair with async donor atoms. So we can observe the donor atoms spins. Therefore, we can detect donor atoms by using charge pumping EDMR method. Finally, I'll conclude my talk. By using charge pumping, we combined the charge pumping method with electron spin resonance method. We call it charge pumping EDMR. By using the charge pumping EDMR, we for the first time identified the defect origins responsible for the charge pumping method. And we clarified detailed charge pumping process. Thank you very much.
Thank you, Professor Hori. So now the presentation is open for discussion. If you have any questions, please raise your hands on the Zoom, and I will call your name, and you can start to ask questions. Any questions? Okay, so I have one question about the shadow state. So in your study, your material has the shadow state in addition to the PB0 state or any other states. So if there are no deep state level, is it possible to recombinate the carrier to the valence band?
It's a good question. To shallow state is not the recombination center. So if there is no deep level, shallow to recombination does not occur by a shallow state. So, but shallow state is very important role because shallow state supplies the electron spin to the defect state. So shallow state and deep level state are both required for the observation of the signal.
Okay. And another question is in order to determine the energy level or energy position of the state, the defect states. So you change the magnetic field, right?
It's also a good question. By changing the energy, we change the gate pulse because I'll skip the detailed explanation, but by changing the gate pulse slope, we can change the energy level. So, so by changing the gate pulse slope, we can change the energy level.
Okay.
Now we detect about the shallow energy range.
Thank you.
Thank you.
Any other questions or comment? So the last question from my side. For other materials like the wide band gap materials, is it possible to use this method?
Yes, thank you very much. Yes, I think it's possible. Now we try to gallium nitride transistor, but it's very it's issue for
yeah.
Now we try to it.
Yeah, maybe the quality of the substrate is also very crucial for the measurement, right?
Yes.
Yeah.
So
the silicon is the most proper material for this kind of test, I think.
Yes, our measurement is more defect. If there are many defects, we can easily detect the signal. So, for example, gallium nitride for the gallium nitride, there are a lot of defects. So we can maybe easily detect the defects.
Okay. Thank you for your comments. Yeah, the time is almost over. If no any other questions, so let's thanks to the speaker again, Professor Hori.
Thank you.
And yeah, and we will move to the next presentation. Could you stop your?
Okay, thank you very much.
Yeah, and maybe wait, Rudra, could you share your screen for the about Shimomura Sensei? Yeah, so the next invited lecture will be given by Professor Masaru Shimomura from Shizuoka University. And he is also working on some materials and especially the atom imaging by 3D photoelectron holography and X-ray fluorescence holography and many other topics he is working on that. Yes, and Professor Shimomura, are you ready for the presentation?
Thank you very much.
Yeah,
so let's
and
share.
yes, and we have to stop the window sharing first, and after that you can start your window sharing.
Okay.
Yes.
Can you see the screen?
Yes.
Okay, thank you.
Thank you.
Thank you very much for the kind introduction, Professor Shimura. And my name is Masaru Shimomura from Shizuoka University. In this presentation, I would like to talk about atomic scale structural analysis by X-ray fluorescence holography and photoelectron diffraction. And in my laboratory, we are doing research on nanomaterials. And also at the same time, we are focusing to analyze the properties of them. And in here, the session title is Manipulation and Characterization of Materials at Nanoscale, Atomic Scale. So now I'm wondering to talk about our knowledge about the atomic scale analysis characterization. So please look at these schematics. I'm sorry. Please look at these schematics. They include how the dopant atoms are incorporated. Here, the pink-colored atoms are showing the dopant, and the green-colored atoms corresponding to the main material. And in here, the first one is the substitutional site model. It substitutes the site of the main material. And the second one is the substitutional, but local structures are a little bit different from the original one. So, for example, such as a dopant and vacancy pair or local distortion is considered in this model. And the third one is this model is based on the local segregation of dopant atoms. And the fourth one is the interstitial site model. In here, it is preserving the initial atomic network of the main materials. So the point is, for example, if we use the XRD type of diffraction, we cannot get the local information like them. We always measure the major materials information. So in this presentation, I would like to explain about the local structural analysis by using X-ray fluorescence and photoelectron diffraction. And for that type of measurement, the combination of elemental analysis and diffraction, That is very important. For elemental analysis, there are two major methods. And one is the X-ray fluorescence, XRF. And second one is the X-ray photoelectron spectroscopy, XPS. In XRF, the emission of characteristic X-rays from a specific element that has been excited by high energy X-ray is analyzed. And on the other hand, in XPS, the emission of photoelectrons from a specific element that has been excited by high energy X-ray is analyzed. So they are very similar. And the difference is the characteristic X-ray detection and photoelectrons. But we have to be sure in XRF, it is very bulk sensitive. The detection depth is roughly 100 nanometer to 1000 nanometer, micron. However, by using XPS, it is very surface sensitive technique. It's like a few nanometer range. So these elemental analysis are used with a diffractional information in this presentation. And this is the energy diagram of XRF and XPS. And they are the core level electrons. And if the sample is irradiated to the high energy X-ray, like this one, then the photoelectron is emitted from the solid. And this photoelectron can be detected by using XPS. And in XRF, the decaying this electron to the core hole, because of this energy difference, we can observe the characteristic X-ray. So this is the basic scheme of XRF and XPS. And during the excitation process, here is an emitter atom of XRF or photoelectron. The emitted photoelectron or photon or electron has a wavy nature. Therefore, they are scattered by the surrounding atoms near the emitter. Because of interference of directly emitted electron wave and also the scattered electron wave, we observe the intensity variation here, depending on the detection angle. We say this intensity map as a hologram. So in other words, if we observe the hologram, then we can have information of the scattered atoms near emitter. This is a basic information obtained from XRF and photoelectron diffraction. In here, I should emphasize that we need single crystal to measure the diffraction. An emitter atom must have similar local structure. It is okay even though the emitter is distributed for the surface and they are separated, but the local structure must be similar in the wall structure. And this shows the XRF hologram formation process. This is a simulated hologram based on the single scattered atom. And like this one, if emitter is here and scatter is there, and then a very strong intensity observed to the forward direction of the scatter. This is the case. And if there is one scatterer, we observe this type of hologram. But if there are several scatter atoms, we observe this type of hologram. But now here, the nearest neighbor atoms are considered. But if we assume the very large cluster, then we will obtain so complicated hologram pattern like this one. And this is the case of gold crystal. And it's a simulated pattern. And this one is the experimental pattern by using the synchrotron. Like this, we can obtain the crystal information near the emitter. And this is a list of history of X-ray fluorescent holography. And from 1996, it took 2 months to get XFH X-ray fluorescent holography measurement. But in 2000, it becomes 6 days by using synchrotron radiation light, very strong X-ray light. And currently, now it takes a few hours to a half day. And in this research, we are trying to obtain the holography by just a second range. Now we are trying to get the hologram pattern less than 1 minute. So objective of the XFH study, we are trying to evaluate the super short time XFH measurement by using large area 2D two-dimensional detector. And let me explain about the experimental setup. This is the 2D X-ray detector that we used. It is made by Rigaku company, and the name of the detector is HiPix 9000. It includes the 775 by 1155 pixels, and each pixel can get the 10 to 6 count rate. And here is a sample, and incident X-ray comes from this way, and it hit the sample, and from the sample, the holographic image is going to the 2D detector. And we used the Spring 8 synchrotron radiation light for the incident X-ray. The experiment was done on beamline 13. And this image shows the partial hologram that is close to the raw data. This is the image on the detector. And here, there is a black line because of the electronics wiring. And this one is the removal data. Black one is removal data because of the X-ray diffraction spots. And now you noticed white lines. They are corresponding to the co-cell lines. Co-cell lines is the this is because of the black reflection from a point emitting process. And there are several, for example, the blue colored line is 110 plane, and this is 210, red color one is 210 plane, and the green color is 200 plane co-cell lines. The sample was ion Fe001 single crystal. Now the detector is located like this, and the incident X-ray comes this way, and from the surface normal, the detector is 30 degree off. This is the position of the 2D detector. And with that data, we try to extend the image to the wall angle by assuming the rotation symmetry. Then finally, we obtained this hologram from this image. And then let me show the data set. This is the experimental data that just I showed. And then the right hand is the simulation diffraction pattern. If you look at the Cosell lines, they agree very well. And the measurement time was just 30 seconds to obtain this experimental pattern. So if we use this pattern, and then we will obtain the atomic image just from 30 seconds, less than 1 minute. And then let me explain about the conversion process, regression analysis process. Here, there is an emitter. And then if there's nothing, then nothing happened. But if we assume several scatterers, then we can convert it to a hologram. Then we compare this simulated hologram and experimental pattern. Then subtract them. Then regression analysis starts. Then scatter position rearrangement was done. Like this. Then we move the positions of the scatterers, then observe the difference between them. And finally, if the pattern becomes similar, then we can conclude the scatter position is agreeing with the experimental and simulation. This is a process of regression analysis. So they are the 3D atomic images of iron single crystal. The above three images are corresponding to the experimental data sets. The green circle corresponds to the ideal bulk Fe atom position. Z equals 0 means it is the same plane as the emitter atom. Z equal 2.9 angstrom corresponds to the plane that 1 unit cell higher, and Z equal 5.7 corresponds to the 2 unit cell higher than the emitter. And the bottom three images show the reproduced atomic image from the simulation. It is a little bit complicated, so let me explain in detail. First, we calculated the simulation image by using full atoms in the crystal model cluster of ion 001. Then using the simulation pattern image like this, hologram, we performed the regression analysis using this simulation pattern. So this even using the simulation hologram, only limited number of atoms are reproduced. For example, this one, this one, this one, this one, and also here, 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 there, there, there. They are reproduced, but not all. That means this is the because of we obtained the atomic 3D atomic image by using one-shot hologram with a single energy. Some atoms have no effect to the hologram intensity with canceling each other during the interference. So only limited number of atoms are observed. if we compare the simulated 3D atomic images and experimental atomic images, the nearest neighbor atoms of the emitter, they are reproduced well. And one layer higher atom here and there, that's also reproduced well. And interestingly, in this plane, the far atoms like them, they are also reproduced. And in addition to that, this atom is also reproduced. But however, for example, here, there is no atoms are reproduced. So not completely same results are obtained. However, the point is, if we look at the position carefully, the reproduced atomic position is very, very precise to the ideal position. So if we focus to the dopant atom like this as an emitter, then we can, if there is a kind of a shift or distortion, we can clearly observe the distortion structure by using this XFH method. So this is a summary of XFH study. Super short time XFH by using large area 2D detector have been examined. Even one-shot XFH data for 30 seconds, the holographic image reproduced from the experiment is almost similar to that from the simulation. Thus, local atomic structure of a targeting element can be analyzed by XFH with a combination of simulation and experiment. So this is the collaborator of this work, Mr. Iwama and Mr. Ono, Mr. Hiraoka. They are the students in my laboratory. And especially the data are obtained mainly from Mr. Iwama. And this is the collaborative work with Professor Hayashi, Nagoya Institute of Technology, and Professor Matsushita, Nara Institute of Science and Technology, and Dr. Kinoshita in Springate. I have a little more explanation about the photoelectron diffraction. So I briefly explain about the results. So in the beginning, I said that photoelectron intensity changes as a function of a detection angle. However, in the case of photoelectron, we can also change the primary X-ray energy. So that means we can change the wave length of a photoelectron. So if we change the incident X-ray, this pattern, the hologram, also changes as a function of the incident X-ray. So we are trying to measure the effect of energy angle scan. This is a very tricky one, but we change the energy and detection angle at the same time by using the one-dimensional analyzer like this one. It is a Sienta Omicron analyzer. It has the plus minus 15 degree, just means the 30 degree range of angle result data can be obtained with this one. And this is a very simple pattern of indium 4D that's just only single indium and phosphorus atoms located like this one. And this is the result of photoelectron diffraction pattern. Interestingly, the vertical axis is the angle for detection angle from the surface normal. 0 is surface normal. And the horizontal axis is the kinetic energy of the and maybe you notice the three spots, three high intensity positions. And this angle, polar angle, corresponding to the indium and phosphorus angle of 54.7 degree. It is just like this one. And also the important thing is the depending on the indium phosphorus distance, we observe the wavy structure along the kinetic energy scale. So this is, it is just like a EXAFS X-ray, extended X-ray absorption fine structure. So we can obtain the information of the bond length and also geometrical information at the same time with this photoelectron diffraction. And this is the simulated photoelectron diffraction pattern with indium phosphorus, indium phosphide bulk structure. Then we can also observe the fine structure along the kinetic energy range. And also we observe the dots depending on the angle of the scatterers. So thus we can obtain the information of the local structure by using photoelectron diffraction. So I skip them, and let me summarize the talk. We used XFH and photoelectron diffraction. They are the very powerful tool to evaluate the local structure of specific elements. And the local structural analysis near the dopant is one of the targeting field of this technique. In near future, I want to give our data of a dopant, near dopant structure. That is our future plan. Thank you very much for listening. Thank you.
Yeah, thank you, Professor Shimomura. Now the presentation is open for the discussion, and if the audiences has any questions, please raise your hand in Zoom, and I will call your name, and you can start your question. And any questions or comments? Yeah, please start, Professor Hori.
Thank you very much for the interesting talk. I have a simple question. Could you tell me the sensitivity of the detection, for example, dopant? Could you tell me?
Just a moment. We are thinking about the dopant density like 1% to 0.1%. So for using this technique, we succeeded to measure very brief time. However, currently it took a few hours to half day. Then now we can obtain the image like 30 seconds. So roughly several hundreds times we can reduce. But in other words, if the amount of emitter is also reduced like a dopant, the intensity is also becoming low. Mm-hmm. So probably if we use this method with a very high sensitive detector, the dopant amount should be more than 0.1%, I guess. Mm. That is the lowest limit of a dopant, I think. Mm. Of course, if we have more time, then it is okay. But usually, for example, by using XPS, the detection limit is also the similar, mm-hmm. the 0.1% mm-hmm. or something, a few 0.5%. So I think it's almost similar. So it is a little bit different from a very tiny amount of dopant like boron in the silicon or such kind of system. That is much less than that.
Okay.
Okay, thank you very much.
Yeah, and the next one, the Professor Moral, please. Moraru Sensei. So you are in mute. Professor Moraru?
Okay.
Yeah.
Okay, can you hear me now? I think I was on mute from organizers somehow.
Yes.
Thank you for the very, very exciting talk. And I'm very interested in holography, your holography approach. It's, I think, quite unique. And I think my question is similar to Hori Sensei's question. So I understand the limitation for detecting dopants in silicon is doping concentration. That's basically it. If we create a extremely heavily doped silicon, is it possible to detect? And my second part is, can we see a difference between donors and acceptors?
Of course, the limit is just, I think, 10 to 20 level. That is a low limit.
Yeah, almost 21. So we can
almost 21. Yes.
Challenge.
Okay. And the second question is
donors and acceptors. If we expect any differences.
Of course, yeah. This is the element sensitive analysis. So we can choose the element. So if we use the different type of element for donor and acceptor, then we can clearly separate them, distinguish. This is a very big advantage of this method.
Okay, thank you.
Okay, so the time is almost over, actually already over. And let's thanks to the Shimomura Sensei again.
Thank you very much.
Yeah, thank you very much. Yeah, and please stop your sharing. Yeah, thank you. And we have the 3 contributed lectures. And the first one will be given by Vanita. Am I correct?
Yes, sir.
Wow. Yeah. And if you are ready, we will stop our sharing and please share your screen.
Okay, sir.
Yes.
So good afternoon, everyone. I'm Vanita, research scholar from.
Yeah. And
Shall I start?
Yes, please.
So I'm Vanita, research scholar, Department of Chemistry, SRMIST, under the guidance of Dr. Jayalakshmi, Professor, Chemistry, SRMIST. So here I'm going to share my topic, the influence of nanosilica and the microstructure of phospho-silaxo geopolymeric network synthesis using metakaolin binder and phosphoric acid hardener. So geopolymer, the name geopolymer was coined by French professor David Dios in 1978 to represent a broad range of materials characterized by the network of inorganic molecules. So geopolymers are aluminum silicates. They are amorphous in nature and it is utilized for construction and infrastructure, whereas it is alternative for OPC as binder. It has less carbon footprint and with less energy consumption. So these kind of inorganic network materials, they are fascinating in now technology, and because they are eco-friendly in nature and low-cost materials. So geopolymers, they are mainly inorganic polymers, mineral molecules linked with covalent bonds, and they are amorphous or semi-crystalline in nature. The source materials were fly ash, GGBS, metakaolin, rice ash, red mud, natural soil, and ash, etc. So activating liquid will be based on acid or alkali. Alkali will be sodium silicates or sodium hydroxide, and or potassium silicate with potassium hydroxide, and acid will be orthophosphoric acid. So geopolymers, geo means the source materials and they are origin from the geological origin which contains silicon and aluminium. Polymers long chain molecules with repeating unit as silicon and aluminium. So alkali-based geopolymers and acid-based geopolymers. In alkali-based geopolymers, silanol molecule where reacted with the base molecules gives the product siloxane anion and water molecule, and that silanol anion again uh, followed by the reaction with the silanol molecule gives the general representation of alkali-based geopolymer. Whereas alkali-based geopolymer, the source materials will be aluminosilicates, and sodium silicate with sodium hydroxide or potassium silicate with potassium hydroxide gives alkali-based geopolymer. An acid-based geopolymer, the silanol molecule react with the acid solution, react giving the product osmium ion, and silanol molecule again react with one of the product of osmium ion gives to the general form of acid based geopolymer. So in acid, again the aluminosilicates with orthophosphoric acid gives the alkali acid based geopolymer. The main objective of the study will be the study the effect of nanosilica in the new geopolymer construction industry, and to evaluate the active nano form of silica in orthophosphoric geopolymeric network to investigate the microstructure under the thermal stress. So materials and methods, metakaolin with phosphoric acid to prepare new kind of geopolymer known as phosphoric acid based geopolymer. In nanotechnology, nanoparticle is an elementary building block and includes up to thousands of atoms in 1 to 100 nanometer cluster. Uh, Whereas nanosilica among all nanomaterials are widely used material in the cement and concrete to improve the performance because of its pozzolanic reactivity besides the pore filling effect. The new technology will incorporate PO4 unit in siloxo chain and produce polyphosphosiloxane network, and there will be partial replacement of silicon by P. These networks are formed by acid-base reaction. So phosphoric acid reacting with metakaolin and reverse and again with nano additive as nanosilica is added and cured for room temperature 24 hours, and again with oven 8 hours at 80 degree. So the required product is generated. So mixed design will be sample ID and nano additive effect. Geopolymer network characterization. So in FTR, in IR spectrum of metakaolin indicates the medium absorption band at 1028, and whereas it attribute to OH bending, and the shifting of SiO-Al band wave number confirm the incorporation of P atom, and hence SiO-PO is formed. Higher the wave number indicates the stronger bond and in increasing the concentration of phosphoric acid. There is a decrease in wave number. Therefore, K8 was optimized. Effect of nanosilica were further studied with the optimized sample. In NS spectra of nanosilica, there is a peak at 1114 centimeter and attribute the presence of SiO-Si asymmetric stretching vibration. A peak at 1075 centimeter was assigned to asymmetric SiO-Si and SiOL, and again 1040 to 1078 there shows a PO stretching and bending vibration. So the samples were treated at 800. There is a shift of wave number indicates the reaction is carried out with the higher and greater mass removal of water molecule completely. The hexad peak of metakaolin shows X-ray amorphous crystalline structures. In phosphate-based geopolymer, a new phase, aluminum phosphate and berlinite, was formed. And while heating, this peak was this. There is a crystalline peak of aluminum phosphate is clearly shown at above 800 degrees Celsius. So compressive strength was there is a clear change in compressive strength where the control mix was less with compressive strength, and with nano additive it has been increased gradually. So same image of metakaolin shows fake-like structure, and there is a microstructure with connectivity of polyphosphosiloxo formation can be seen in the K8 samples, and this could be related to the break. Some cracks are also visible, and this could relate the breakage of integrated structure during the compressive strength. And because of nanosilica, the samples become pozzolanic material, and the spear-like shapes can be visibly seen in the K8b samples, and this converts the formation of a hot block of polyphosphosiloxo formation, and with nanosilica it becomes more homogeneous and denser matrix. So conclusion, phosphoric acid solution with different molar ratios are prepared and used for phosphoric acid based geopolymer. The influence of molar concentration of phosphoric acid solutions on mechanical microstructural properties of were studied. The FTR increase in wave number of the band decreasing the molar concentration, indicating the deprotonation of orthophosphoric acid. The X-ray pattern shows the amorphous and semi-crystalline peak of aluminum phosphate. There is an increase in the compressive strength upon addition of nanosilica to phosphoric acid-based geopolymer matrix. Some micrographs shows core structure, and connectivity of polyphosphosiloxane formation was confirmed at. The design material is used for low dielectric properties, insulated encapsulating materials, and for electronic packing. Thank you.
You can continue to share your screen. And now the presentation will be open for the discussion. Any questions? Is there any questions?
I want to ask you, Vanita, one question.
Yes, sir.
So what's the, why this, you have chosen this work, or why this work is important for you?
Sir, in geopolymer industry, this kind of acid-based geopolymer is fascinating technology nowadays. So I've taken the acid-based geopolymer
No,
chemistry.
fascinating for what reason? Why it is fascinating?
There are less literatures compared to alkali based. So acid is comparatively less, and compared to alkali, acid gives more thermal resistivity, and it is also used for dielectric properties also for dielectric materials.
Okay, thanks.
Any
Thank you,
others?
sir.
So I have one question. What is the most important parameters to be controlled for synthesize the better materials?
Sir, aluminosilicate source when reacted with acid, it gives a phosphoric acid based geopolymer, sir. Conditions will be at there will be cured at room temperature and again at oven at 80 degrees Celsius.
Yeah, yes. So I know the conditions, but what is the most important parameters or conditions? The temperatures or time or what is the most important conditions to be controlled?
So there will be condensation reaction carried out while
Mhm.
keeping at room temperature for 24 hours, and after that polymerization reaction is carried out where the polyphosphosiloxane chain has been formed.
Okay. Thanks.
Thank you, sir.
So yeah, if there is no any questions, so let's thanks to the speaker again, and let's move to the next presentation. So next presentation will be given by Mr. Alvin.
Yeah, I'm here.
Yeah. So you can start your presentation. Please share your screen.
Can my screen be seen?
Wait. Maybe you put the Zoom window on your PowerPoint. It's all.
Can my presentation be seen? Yeah.
Almost. Some window is overlapping on your screen, maybe.
Oh, some window. Okay, wait. Sorry.
Yeah, this one.
Oh, okay. I'll push it down. Okay. Is it clear now?
Yeah. On the top of the screen, you still have some window, right? Yeah, this one.
Okay, wait. Oh, okay. How should I remove this?
Complicated.
I'm sorry. Okay. Is it okay now? No.
Okay. Please start.
Okay.
Yeah.
Okay. Okay. Good day, ladies and gentlemen. My name is Elvin. I'm from Kyushu Institute of Technology from the Graduate School of Life Science and System Engineering. So the topic of my presentation is facile fabrication of three-dimensional cuprous oxide, titanium dioxide, cellulose, nanofiber reduced graphene aerogel with enhanced photocatalytic activity. So before I move on, I think it's important for me to explain the graphene hydrogel formation because this is going to be the template to orientate my photoactive material. So the most of the time, graphene oxide is used as a precursor due to their ample of oxygen functional groups at their basal planes, which enables them to interact with other chemicals easily, and they have really good dispersity in various solvents. So oftenly, the formation of graphene-based hydrogel is via two kind of method, which is via the chemical reduction method using ascorbic acid or using the hydrothermal method. So among the salient properties of this graphene hydrogel is it's of porous network structure, and it can able to orientate catalysts or photocatalysts, and it is low in density. So the figure shown here is being published like 11 years ago, indicating the formation of gel using the hydrothermal method. So most of the researchers posit that the formation of hydrogel is actually driven by strong hydrophobic and also pi-pi stacking interactions of the sheets. So when we talk about graphene-based hydrogel, that in terms of application-wise, water purification application has been the usage of graphene-based hydrogel has been rampant in water purification application, besides others such as supercapacitors, in the biomedical fields, and so on and so forth. So in previous studies, we found that these two materials here, the titanium dioxide and cuprous oxide, they are actually good photocatalytic, they possess good photocatalytic activity. And why do we use nanocellulose in this research? Because previously it has also been reported that the nanocellulose network will surround the graphene sheets and improve the water transport properties. So these water transport properties is important in waste remediation application. And previously also it has been reported that cuprous oxide quantum dot, reduced graphene oxide, titanium dioxide has been synthesized using hydrothermal method, showing excellent photocatalytic performance in the degradation of several dye compounds. So let's move on to the methodology. First of all, our strategy, first we prepared cuprous oxide nanosphere using the green reducing agent, which is glucose, and then a simple method to prepare the nanosphere cuprous oxide. And then while for the preparation of the modified improved graphene-based hydrogel, first we have the graphene oxide suspension added in with the cellulose nanofiber, and then sunnicate it in order to form, to create this kind of formation of bonding. And then we add in our photoactive materials, which are the titanium dioxide and also the cuprous oxide, undergo sonication again, and then undergo the hydrothermal treatment, and we get a modified hydrogel. So after freeze drying, we could see the structure of the hydrogel here, which has been oriented by the titanium dioxide and also cuprous oxide, and we use it to carry out photocatalytic degradation of dye molecule, which is the metal orange. So let's take a look at the SEM image, which portray the morphology. So figure A shows the clear indication of the formation of nanosphere. B is the annotated structure of the titanium dioxide, which is commercially bought. And C is our graphene-based sheet without any presence of cellulose or the photoactive material. And we can see a clear differences between the morphology after the inclusion of the cellulose nanofiber, which causes the sheets to be much more crumpled, which is we posit due to the effect of the cellulose nanofiber. And then the orientation of cuprous oxide, the cuprous nanosphere on the graphene sheet and cellulose nanofiber, and this is only with titanium dioxide, and this is with the presence of both photoactive materials, which is the cuprous oxide and titanium dioxide, on cellulose nanofiber and reduced graphene hydrogel. So the EDX further confirm the presence of these two photoactive material on our hydrogel. Accessing the crystalline structure of our hydrogel, first of all, our crystalline structure of the prepared cuprous oxide confirmed to the previously reported indexing, indicating the peaks at these respective peaks here. So same goes to our titanium dioxide, and our cellulose and graphene base sheet indicates a peak at about 23 and about 43, which is very common for most carbon material. So after the orientation of the protective material, we could see the sheets, the graphene sheets at 23 collapse. This is possibly due to the presence of this protective material closing down or inhibiting the the showing of this particular peak here. So our Raman spectroscopy for the reduced graphene hydrogel modified with the photoactive material shows an increase in the ID-Ig band, indicating that the graphene sheets, there was some form of defect presence at the graphene sheet with the orientation of these two particular protective material. So moving on, in our application wise, we tried using metal orange as our dye pollutant. So we could see when we compare our graphene, the modified reduced graphene hydrogel gives the best photocatalytic performance. While in terms of the kinetics, you can see they managed to degrade metal orange up to 85.62% under 120 irradiation. So we also carry out the different effect of photocatalytic performance, which is the pH. So we found that it's best under neutral pH, about 7.3. And also, while we also studied the effect of concentration of dye, so the lowest concentration of dye exhibited the best performance, possibly due to too many metal orange, will eventually will actually block the UV light that actually for them to perform best. So finally, when we carry out the antibacterial effect, because while it's important also in antibacterial effect, the formation of biofilm on the surface of the catalyst will inhibit the catalytic performance. So this is done in dark conditions. So we can see F here, we can see there's even a total kill of E. coli, indicating that our material here exhibited antibacterial performance, even without UV radiation. So in conclusion, we managed to prepare cuprous oxide titanium dioxide modified on CNF RGH via the fissile hydrothermal treatment and freeze drying. And then we believe that the CNF improved the homogeneous anchoring of the cuprous oxide and titanium dioxide on the cellulose nanofiber graphene sheet. And lastly, the photocatalytic degradation performance is enhanced for this modified hydrogel and also exhibited good antibacterial activity. So with that, I thank you.
Thank you for your presentation. And is there any questions? Yeah, you don't have to stop sharing. Yeah. Anyway.
Oh, okay.
Yeah. I have a question about the band diagram.
The band diagram. Okay. Mm-hmm.
Yeah. And in this composite, what kind of band diagram was formed?
Okay. Because for this is an ongoing research, so we have not conducted the UV-DRS yet for us to access the band diagram of our graphene based hydrogel. So I think once we are able to get the UV-DRS band gap, then we will be able to somewhat draw the band diagram of this particular hydrogel.
Yeah, from some literatures, maybe you can predict the band diagram of your composite already. And to think about why the efficiency is increased by this composite, it's necessary to consider the band diagram anyway.
Yep.
And
Thank you
also,
for the suggestion.
Yeah. Then, so for the band diagram, in terms of the band diagram, maybe you will have to control the band offsets. I don't know, just a comment. But then, so next time, please consider the band diagram also.
Yeah. Okay, I will take that into consideration and also carry out additional, because this is an ongoing work. So thank you for the really good suggestion on to determine the band diagram, the band gap of our particular hydrogel.
Yeah. So I have a short question.
Can I have
a short question, please?
Yeah, Mr. Alvin.
Yes.
This is very much related to what Professor Yosuke Shiromo has already asked you about the band gap. You have studied the photocatalytic activity of your material, right? So what was the source of light that you have used?
UV light. So we are using xenon lamp, So that is used for UV curing of, actually our lamp is used for curing polymer-based sheets.
Okay.
So we are using, because that's only our source of lamp. So in our case, because we know that TiO2 will be able to, they are within the UV range, while for the cuprous oxide, it's more towards the range of visible light. So we believe that the inclusion of these two material, protective material, will somewhat reduce the band gap more.
Yeah, that's what I'm also interested to know. Since you have incorporated Cu2O into or onto TiO2, the band gap will definitely change.
Yep.
It would be somewhere in between that of Cu2 and TiO2.
Yep, correct. Very true.
So I would also recommend you to find the band gap so that you can give a try whether you can use this material for visible light photocatalytic applications.
Yeah, thank you so much for the really good suggestion.
Yeah.
Okay. The time is over. So please, let's thanks to the speaker again. And yeah, we need to move to the last presentation. So please, Mr. Alvin, please stop your sharing.
Yes. Okay, thank you so much.
Yeah, and Mr. Chandorika is there?
Miss Chandrika. Mrs.
Yeah,
Chandrika.
Yeah, sorry. Yeah, please start your presentation and start your sharing.
Okay, sir. Is it visible, sir?
Yes.
Okay. Good afternoon, everyone. I'm Chandrika, research scholar from KLEF, Guntur, Vijayawada, Andhra Pradesh. Working under the guidance of Dr. A. Venkat Ravindra, who is Assistant Professor in Department of Physics, SRM IST Chennai. And I'm thankful to Dr. Xiaohua Zhu and Shui Wong for facilitating photocatalytic experiment. So today I'm going to talk about starch-assisted green synthesis of nanoferrite and nanoferrite semiconductor composites for photocatalytic degradation of methylene blue. So the water body that you're going to see, that you're seeing here, is not some exotic place, but it is caused due to the dye water or the wastewater that is dumped into the water bodies from the textile industries. And it is a grave issue of concern because this issue is persisting because lack of effective ways or effective methods to combat this issue. Even if we come up with effective methods or treatment, they are quite expensive, and still these expensive treatments have their own harmful byproducts, and certain dyes are still not degradable, which add to the contaminants already present in the water, and which is life-threatening, which causes life-threatening diseases to all forms of life on Earth. So photocatalysis is a effective method we have that has come up with solutions to address all these issues. So photocatalysis is a process similar to photosynthesis in nature, where the photocatalyst, that is chlorophyll, which will take light and carbon dioxide and water and to form it and to form convert that to carbohydrates and oxygen, which is safe and useful to the environment. Similar process in photocatalysis, we have photocatalyst, that is, we use here nano photocatalyst, which will take light and it will give rise to hydroxyl and superoxide radicals, which are very powerful to combat with the organic, even non-degradable and toxic pollutants, and convert them and break them into non-harmful and safe compounds or to carbon dioxide and water. So the process that is actually happening inside a photocatalyst is we have a band gap for the photocatalyst material. So whenever it takes the light is incident upon it, whose energy is greater than or equal to the band gap of the catalyst, what happens is the electrons from the conduction band will get excited to the electrons from the valence band will get excited to the conduction band, and there is separation from between electrons and holes. These electrons will, when the photocatalyst is put into the water, it reacts with water and oxygen to give superoxide radicals, and similarly the holes in the valence band will react with hydroxyl ion to give hydroxyl radicals through oxidation and reduction process, and these radicals will in turn help us in breaking the contaminants to harmless compounds. So we know that most widely used photocatalysts are semiconductors, that is TiO2, titanium dioxide, and zinc oxide. So, but they have their own limitations that after the water treatment, they need to be removed pulled out from the water treatment barrel, so which is very difficult. And also they have limitation with the amount of solar energy utilized for photocatalysis. So this is addressed by using magnetic particles, that is ferrite, so which will help in tuning the band gap of these semiconductors to bring down to visible light spectrum. And also they will help these nanocomposites to be pulled out, or these semiconductors to be pulled out from the water after the treatment, and which can be further recycled or reused for further treatment of the water. So this is making it safe and cost effective. Also, there is no much harmful byproducts that is formed in this process. So keeping in this view, we have synthesized composites using ferrite and ferrite composites with ZNO and TiO2 semiconductors. And so the first three samples is as prepared samples, and we have annealed the ferrite and TiO2 nanocomposite which is microwave annealed at 500 degrees for 10 minutes. So we have used these composites to test on methylene blue, which is an organic dye with bright blue color. So coming to the synthesis process, so we have used starch here, which is a biodegradable polymer and has an important place in food industry, and to promote it promotes green synthesis. So we have used starch, and we have prepared the ferrite particles, nanoparticles already, and we have used these ferrite nanoparticles along with the semiconductor precursors. So the semiconductor precursor can be with respect to TiO2 and ZNO. So here the role of starch is that of the surfactant. So we have combined these three and put it for stirring for 1 hour, and then we have used reducing agent sodium hydroxide to form the hydroxides, and the resultant is put for 2 hours at 90 degrees centigrade. Then it is washed and dried. So all these three samples are as prepared samples, and this sample is further annealed for 500 degrees and 10 minutes. So this is a XRD pattern for FFO and ZFO. So for FFO, we have got, you can see the corresponding JCPDS files here. So this is the FFO XRD pattern, and this is the ZFO XRD pattern, nano composite. So we can see that we have got the pure phase for FFO, that is cubic spinel, and for ZFO hexagonal bullseye. But coming to TFFO, we can see that there is another impurity phase, that is because of sodium iron, that is monoclinic sodium iron titanium oxide. So because of, if you look at TFFO as prepared sample, we can only see some crystalline peaks of FFO phase, but not of TiO2 phase, which is in amorphous phase. That is the reason we have annealed it to, microwave annealed it to 500 degrees for 10 minutes. So now we can see the crystalline phase of monoclinic sodium iron titanium oxide along with the FFO phase here. So So the reason for formation of sodium iron titanium oxide is maybe because of the presence of sodium hydroxide, and which interact with titanium, which interact differently with titanium dioxide in the presence of iron oxide particles. Then we have TEM images for FFO and ZFO particles. So this is corresponding to FFO particle, and this corresponds to ZFFO particle. So we can see here that the morphology that we got here is a mixed morphology of spherical and spherical particles and some nanorods. You can see some nanorods inside here. Similarly, TEM for TFFO, this is for TFFO as prepared, and this is for TFFO microwave annealed. And here also we will get some spherical morphology and rod morphology, but the density of number of nanorods in TFFO is greater when compared to other as prepared samples. And we can also see that these nanorods are uniformly shaped and are more in number when compared to other particles. So you can see the result here. So in FFO, this is the average size of the spherical particles, and this is the average length and diameter of the nanorods found in all the samples. So here you can see ZFFO has a big nanorods, but the number of nanorods is very less when compared to TFFO microwave annealed, which has a size comparable to that of FFO, but because of annealing, it is slightly greater than this.
The time is over. So now we have to move to the discussion, and please just go to just go to the conclusion slide.
Okay. So this is a BET analysis where we found that.
Okay. No. Just go to the conclusion slide page.
So here we can find the first order kinetics is giving more R square values. So it is best defined by the first order kinetics, and TFFO has more R square value. So you can see that TFFO MFA is giving 99% of degradation in 90 minutes when compared to other samples. So coming to the conclusion, so we have got that is the phase of FFO and sodium iron titanium dioxide. And we have also discussed the TEM micrographs, and BET shows the structural. We have got maximum pore diameter for TFFO, microwave annealed, and greater degradation for of 99% methylene blue degradation in 90 minutes for TFFO microwave annealed samples. Thank you.
Yeah, thank you. And if there is any questions, please raise your hand in Zoom. Okay, I have a short question about the magnetism. So your material exhibit the magnetism?
No, we haven't tested for that, but we have tested in the lab, sir. We have used the magnet directly, and the samples are, we could separate it easily. But we have not made the measurements.
Mm-hmm. But you succeeded to prepare catalyst having the magnetism.
Yes.
Yeah. So what is the next challenging? So improving some efficiencies?
Yes, sir. Improving the efficiency, and also to address how these are actually contributing to the this degradation of dye, because there is involvement of starch, the effect of sodium ions, and these are which are contributing to the catalytic side, because we can see that if TFFO microwave annealed is not having much surface area, but still it is able to degrade the things. So it means it has more catalytic sites, and it is and because of the involvement of starch and sodium ions, we can see in UV the absorption wavelength is varying. So we should really look into what is actually contributing to these results.
Okay. So the time is coming, and the Mrs. Chandolika, please see the chat window by yourself, and the reply to the Gayasri, Mr. Gayasri, later. So what is this noise? Yeah. Yeah, and so this session is all completed. So thank you for your attending, and we delayed a lot, but now the keynote lecture is ongoing. So please attend that lecture also. Thank you for your coming.
Thank you for Professor Shimura for chairing the wonderful session. I also want to thank the participants, Professor Hori, Professor Shimomura, Nita Zeng, and Chandrika. Thanks for attending and all your beautiful and illuminating talks. So thanks. So the session 6F of ICONN 2021 concludes with this. Thank you.